When we first started talking about the three states of matter, I pointed out that gas molecules are so far apart and moving so fast that their attractions between the molecules or particles are negligible. So when we talked and learned about gases and some of their properties, we did not discuss the attractive forces. However, as we transition into talking about liquids and solids, we have to bring up this idea of intermolecular forces. So intermolecular forces are the attractive forces that exist between molecules. So intermolecular, between molecule forces. I imagine molecules as being little magnets. And you know how magnets, when you have them together, they can be attracted to each other. Well, all of these forces that we're going to discuss have a similar, that analogy works very well. It's like they're little magnets. Now, these three are in order in this list, starting with the weakest first. So you see London, dispersion are the weakest. And as we go down the list, the dipole-dipole is moderate into hydrogen bonding, which is the strongest. And the strength of the intermolecular forces help us understand some of their properties. So the first one is London dispersion forces. This, as I mentioned, is the weakest force, and it occurs because of temporary dipoles. So a dipole is when you have a separation of charge in the molecule. So I kind of imagine this is related to a polar bond, and I imagine a dipole being a situation where the electrons cause, remember the little partial signs, one side to be partially negative and one part of it to be partially positive. And so the charge is not equally distributed, but instead it has two ends, dipoles. So in London dispersion, these are temporary dipoles. So temporary dipoles, if something's temporary, it means that it is not constant, but it's kind of on and off. So this makes it the weakest. Now, where these temporary dipoles come from is kind of hard to imagine. At any one instant, the electron density may not be completely symmetrical or even. If more electron density is present in one region than the other, then that side would be a little negative and the other side would be a little positive because the electrons are moving around. So at any given instant, you may have areas of slightly positive and slightly negative. Now, all molecules have electrons. So if you look here, all covalent molecules have these type of forces. However, and I put a star here, this is the only force that occurs in nonpolar molecules. So you might want to go back and review polar and nonpolar. But a nonpolar molecule is one where the electron cloud is evenly distributed around the atoms. And so as it's evenly distributed, we don't tend to have a building up of the positive and negative, except in this motion of the electrons that creates the temporary dipoles. So there's several categories of nonpolar molecules that are very common. All of the diatomic, so over here on this side, I'm going to write some examples. So all of the diatomic elements, so if you have two of the same element, so for example, I'll write one. If I had Cl2, if you have two of the same element, they're going to share the electrons equally, which means that they would be nonpolar. So any diatomic element is always nonpolar. Another category are what we call hydrocarbons. And hydrocarbons are any molecule that contains only hydrogen, and carbon. And it could be big or small. So it could be something like CH4, that only has carbons and hydrogens, or something bigger like C6H14. Now notice over here that if you have a larger molecule, even if they both just have London dispersion forces, the bigger they get, the more surface area they have, and the stronger that London dispersion force will be. So diatomic elements are common nonpolar ones, hydrocarbons, and then other molecules like carbon dioxide or carbon tetrachloride. If you recall, when we were discussing nonpolar molecules in a previous chapter, we kind of looked at their Lewis structures, and if the central atom did not have a lone pair and was surrounded by all of the same element, then it was considered a nonpolar molecule. So things like carbon dioxide and carbon tetrachloride are actually pretty common nonpolar molecules. I find it beneficial for London dispersion forces, especially to remember that diatomic elements and hydrocarbons are always nonpolar. Now the second type of force is the Dipole-Dipole force. So I just described up here a dipole, and a dipole simply means that you have a separation of charge. Now the difference between London is they are temporary dipoles. But the dipole-dipole is a permanent dipole, which means it's always present. This occurs in polar molecules. Because if you recall from this diagram below, like here's HCl, chlorine has a higher electronegativity, so it pulls the electron cloud toward it, and it becomes negative. Hydrogen has a lower electronegativity, and it becomes positive. You can see I kind of tried to draw the electron cloud like that. It's unevenly distributed. If another HCl is nearby, this will do the same thing, and the electron cloud goes by the chlorine. The chlorine is negative because it has a higher electronegativity. The hydrogen is positive. And look, positives, opposite charges, attract. So this little attraction, which I just have drawn as a dash, is what we call the dipole attraction. So it's the attraction of the negative from one molecule to the partially positive part of another. Because it's permanent, it really is like magnets, and it's stronger because it doesn't go away. So molecules that are polar commonly have things like they might have an lone pairs on their central atom, and one that would be something like pH3. So if we looked at its Lewis structure, it would look like that. Or another molecule like this is CH2O. And remember, when we're thinking about this, if your central atom is surrounded by different elements, it causes the electrons to shift like they did here. So something like CH2O, where the carbon doesn't have all the same elements, would be polar. We could have things like HCN, where the carbon has H on one side and N on the other, which makes it not share equally and makes it polar. So when you're thinking about identifying polar molecules, you want to try to consider, do I think that those would share equally? And finally, the easiest one to identify, and so it's usually what I try to identify first, is hydrogen bonding. Now, it really is an intermolecular force. It's not a bond. It's very common in biological systems, and so it's an important intermolecular force. And here is the rule, and this is what makes it easy to identify. Hydrogen bonding occurs when a molecule has one of three bonds in it: a hydrogen to a nitrogen, a hydrogen to an oxygen, or a hydrogen to a fluorine. And in another molecule, you have those same 3 elements. So in this case, we need to have nitrogen, oxygen, or fluorine. And more specifically, we need to have hydrogen attached to one of those. So you can look at the molecule and decide. So if I had CH3OH, here's an oxygen attached to a hydrogen, that would have hydrogen bonding. We also have water, H2O. So we have in water, remember, we have hydrogen attached to oxygen. Or ammonia, NH3, hydrogen attached to nitrogen. So it's very specific rules for hydrogen bonding. You have to have hydrogen that is bonded to one of the 3 most electronegative elements, nitrogen, oxygen, or fluorine. We're going to look in the next 2 slides to see if we can try to predict which type of bonding different molecules have. And I want to tell you, I always try to do hydrogen bonding first. That way, if I eliminate that it does not have hydrogen bonding, I've narrowed my choices down to 50-50. So let's take a look. So in this question, it says, what are the types of the intermolecular forces present in each of the following? So this is a diatomic element, and any diatomic element is considered nonpolar, and all nonpolar things only have London dispersion. Now letter B. So I asked myself first, for hydrogen bonding, I have to have hydrogen to nitrogen, hydrogen to oxygen, or hydrogen to fluorine. This one does have hydrogen and nitrogen, but they're not bonded together, so it's not hydrogen bonding. Now, so then my question is, polar or nonpolar? That's what I would ask next. Now, to be polar, you would have either lone pairs on the central atom, or in this case, I look, and the central atom has 2 different elements around it. That makes this one polar. I didn't mean to erase the polar. And so elements that are, molecules that are polar have dipole-dipole attractions. Now, this is the main type, but some of your homework asks you to name all of the types. Now, if you have London dispersion, only the weakest force, that's all you can have. But intermolecular forces are cumulative. So, if you have dipole-dipole, you would also have the weaker one, London dispersion. So let me make a little list up here so we know we have London dispersion is the weakest. Then I have dipole-dipole. Then I have hydrogen bonding. So what I'm saying is, if I have hydrogen bonding, I actually have all 3. If I have dipole-dipole as my main one, I only have 2. And if you have London dispersion, you only have London dispersion. So in this question, in your homework, it's a drop down. And if it says all types, then it wants to have all of them that are included. So I'm going to answer these like it's asking for all types, just to give you an example. So letter C, I see HF. And I notice that H attached to F is hydrogen bonding. These are my little hydrogen bonding ones. So this guy has hydrogen bonding. That's the strongest force. That would be the most influential. If they wanted to know all types, remember hydrogen bonding, has all 3. So it would also include dipole-dipole and London dispersion, if I had to list all of them. And I am underlining the one that is the main contributor. So that if it only has one answer, you'd only choose the main contributor. Now letter D. CH3Cl. So here's my central atom, and I see that it has 3 hydrogens and 1 chlorine. I don't see any of my hydrogen bonding elements, so I know it's not hydrogen bonding. So I have to decide, is it polar or nonpolar? Nonpolar molecules are surrounded by all of the same elements. So this guy has different elements around it. That makes it polar. So any polar molecule is going to have them as the main force, dipole-dipole. And then if they want all of them, remember it's cumulative, so dipole-dipole will also have the one below it, which is London dispersion. Now notice B and D were both polar molecules, and they both have the same answers. Now letter E is H2, which is a diatomic element, just like letter A. So diatomic elements are nonpolar. And nonpolar only have one force that's a part of them, and that's London dispersion. And so notice again, A and E, when you're nonpolar, you have the same answer, just London dispersion. And then letter F, this guy is a hydrocarbon. And I have memorized that all hydrocarbons, if they only contain hydrogen and carbon, are nonpolar. So because this is nonpolar, it only has London dispersion. So all nonpolar ones only have London dispersion. So nonpolar molecules only have London dispersion. If you're a polar molecule, your main force, attractive force, is dipole-dipole, and you also would have London dispersion. If you have hydrogen bonded to nitrogen, hydrogen bonded to oxygen, or hydrogen bonded to fluorine, then you have hydrogen bonding as your main force, which would include all 3. You would also have dipole-dipole and London dispersion forces. Now, which one of these is stronger? So now we have to identify what type of force. So letter A, carbon dioxide. So carbon surrounded by 2 of the same. This is nonpolar. So it has London dispersion. And water is hydrogen bonding. It has an O and an H. So hydrogen bonding is stronger than London dispersion, so this one has the stronger intermolecular forces. Carbon dioxide we already determined is nonpolar, it's London dispersion. Now HBr, it has an H, but it's not hydrogen bonding because it would have to be attached to a nitrogen, oxygen, or fluorine. And since it's 2 different elements, they won't share equally, so this guy is polar. And polar bonds have their strongest force of dipole-dipole. So dipole-dipole is stronger than London dispersion, so HBr. Now if I compare the dipole-dipole to water, which is hydrogen bonding, then the water wins because hydrogen bonding is stronger than dipole-dipole. And then letter D, I included on purpose. These are both hydrocarbons. And hydrocarbons, I've memorized, are nonpolar molecules. So this would be London dispersion and London dispersion. And so then you think, well, how would I know which is stronger? If they both have the same force, then as a general rule, the larger molecule has stronger forces. And so that means one with 2 carbons and 6 hydrogens would have stronger intermolecular forces than the CH4. Now there's one last thing that I like to point out when we're talking about intermolecular forces. And I like to just look at water a little closer. This question almost always ends up on an exam, either in as an exam question or as an extra credit question. So the Lewis structure, water is a bent molecule, And oxygen has a greater electronegativity than the hydrogen, and with the lone pairs on oxygen, oxygen becomes negative and the hydrogens become partially positive. Basically, all the electron clouds are moving toward this oxygen. So if I were to draw a hydrogen bond between two water molecules, I would draw another water molecule, and the oxygen of the other water molecule would be close to the hydrogen. The reason is the positive is attracted to the negative, and that right there is the hydrogen bond. Now, it's not magic or some special thing that I drew the water molecule there. If I wanted to draw a second water molecule next to the oxygen, I would have to make sure that I drew the hydrogen closest to it. Because the hydrogen we always need, when we're thinking about this, we need the positives and the negatives next to each other. So there's an attraction between the positive and negative. Hydrogen bonds are actually just a special type of dipole-dipole attraction. They are just extra strong because they involve the three most electronegative elements.